In this worksheet, we're going to be starting, in this video, we're going to be starting section 10.1 on worksheet 6. And in section 10.1, we are doing like we did with two sample t-tests, except for now we have a two sample z-test. So we're introducing a categorical explanatory variable to better understand our categorical response. So, for example, before we wanted to understand, did babies prefer helpers or hinderers? But there was still a lot of unexplained variability there. We might want to know, why do babies have this preference? And so maybe, are there differences due to gender? Or in that example, there were only 10-month-old infants, but maybe there was a difference based on age. So maybe 10-month-old versus 11-month-old. Maybe there was a difference as babies aged by 1 month for those two different groups. So what we're going to do is we're going to look at these data from this Frank's sign example, and we want to know, is there an association between two categorical variables, a categorical response and a categorical explanatory variable? Now, I'm going to warn you, dealing with a categorical response variable can be really tricky. It's really tempting to make the levels of the variable itself. So we're going to take a lot of time with these future examples and work on that, especially when the variable is binary or only has two outcomes. So for this example, a 1973 study described an association between earlobe creases, ELC, with coronary artery disease, CAD. A follow-up study in 2005, and if you're interested, I have a footnote with that data, with the reference. A follow-up study in 2005 compared 80 patients with CAD, coronary artery disease, against 30 patients without, where each person in the two groups was inspected for earlobe crease. The results are provided below. So this is called Frank's sign because it was a Dr. Frank who first identified this possible association in 1973. So what is our explanatory variable in this study, and what is the response variable? So identify the variable and then also identify the levels, and then what is the response variable and identify the levels. Pause the video and then pick back up and see if you got the same results as me. So our explanatory variable is CAD, or coronary artery disease. The variable is the disease. The levels are the patient has it or does not have it. So the levels are having or not having it. For example, if we said the variable is that the patient has coronary artery disease, then that means that everyone has coronary artery disease, and that is not a variable. So a variable, remember, is something that varies from one participant or one subject to the next. And so the disease can vary. A patient may or may not have it. So it has to be something that can vary. It is a characteristic, having or not having. Similarly, the response variable is earlobe crease. The levels are having or not having an earlobe crease. And I've illustrated here with a picture what an earlobe crease is. So an earlobe crease is literally this little wrinkle in the lobe of your ear. And what happens every year that I do this example is that everyone comes back to class the next day and they've checked, or they start feeling their earlobes because they're worried that they're going to have coronary artery disease. It becomes more pronounced as you're older. It can happen to both men and women, males and females. But don't freak out about this, all right? So I do this too, like I do this example and I start feeling my ears. But I would like, just, drop me a line or drop me a note on GroupMe if you start feeling your earlobes because you're worried about this, because I just think that's humorous. All right, so these are our two variables. So the response variable is earlobe crease. The levels are whether the patient has it or doesn't have it. The explanatory variable is coronary artery disease, and again, a patient may or may not have it. Here are our data. So we have our explanatory variable on the rows, and we have a response variable along the columns. And this is just called a two-way or contingency table. So this is a two-way table or a contingency table because there are two ways that we can classify our patients. We can classify them based on whether they do or don't have coronary artery disease, and we can also classify them based on whether they do or do not have ELC. And then when we look at all four of those possible combinations, we can get a sense of the distribution, the overall distribution of these patients. So what I have is I have provided the total number of patients who have coronary artery disease. I've also provided the total number of patients who don't have coronary artery disease. And then I've given you the some contingency results. I've given you the total number of patients who both have coronary artery disease and earlobe crease, and the total number of patients who do not have coronary artery disease and have earlobe crease. What I would like you to do is pause this video and complete the rest of this table. So there are 4 more elements that need to be completed. So please fill them in, and when you come back you can check your work against mine. So the total number of patients who have coronary artery disease but don't have ELC is 32, and you can do that by taking the total for that row minus 48. So 80 minus 48 is 32. You can do the same thing for the patients who don't have ELC and don't have CAD. So that's 30 minus 9 is 21. And then to get these last two elements, the total ELC and the total who don't have ELC, you can just add up in that column so you can get the column sums. So 48 plus 9 is 57, and 32 plus 21 is 53. I hope that you were able to get those results on your own as well. So what we want to do is we don't want to compare these raw numbers, because if we were just to compare the raw numbers, we're interested, remember, in the relationship between ELC and CAD, and we don't want to just look at 48 versus 9 because we can see that the overall number of patients who do and don't have CAD is very different. So it's much better to look at the sample proportions. So if there is an association, then the sample proportions for those two groups should be different. So we're going to look at P1 hat and we're going to look at P2 hat. So P1 hat is 48 over 80 and P2 hat is 9 over 30. 48 over 80 is 0.6, 9 over 30 is 0.3, and we can see that just by looking at these two proportions, so of the people who have coronary artery disease, only 60% of them also have ELC. Of the people who don't have coronary artery disease, so of the 30 people who do not have CAD, 30% of them have ELC. So these two proportions, these two row proportions are in fact different. But the question is, how different are they? We have two possible explanations for these results. Well, one of them is that the differences observed, or any differences we observe from this study or any others, are just due to chance. This is the same possible explanation we saw when we looked at the two-sample test for means. You know, in that case we observed differences in means for the M&Ms, right? And that could have just been because we happened to randomly just by chance, get a different mean number of plain and peanut M&Ms per pack. That can happen. In this case, that would translate to our null hypothesis, but now we're comparing proportions. So in the population, pi1 and pi2 would actually be the same. So the true proportion of people who have CAD and have ELC would be the same as the true proportion of people who don't have CAD and have ELC. That would mean that there is no relationship between having an earlobe crease and coronary artery disease. Or the other possible explanation is that the differences observed are due to an underlying association. That's the only other possible explanation. And in that case, we would have to write our alternative hypothesis. And that would mean that pi1 does not equal to pi2, that there is an association that systematically means that these two proportions in the population are not the same. That would mean that having coronary artery disease is associated with having an earlobe crease. And that means that having an earlobe crease or having coronary artery disease changes the probability of having an earlobe crease. Now, I'm not going to say causes that change because this is not an experiment. We can't give someone an earlobe crease, or we can't give someone coronary artery disease to see if there's a driving component, but we can at least investigate and see if there is an increased risk based on the data that we have, if there is at least a correlation or an association between these two variables. So this is kind of like a regression question. Is there a relationship? But we also have to define our proportions. We have to define our parameters in order to complete our hypotheses. So where pi 1 and pi 2 are the true probabilities of having earlobe crease for people who do and do not have coronary artery disease, respectively. So now I've defined what the probabilities are I'm interested in, and I know which group is which. So group 1 is people with coronary artery disease, and group 2 is people without. I'm interested in comparing the proportion of people with and without coronary artery disease and whether they have earlobe crease. So how can we investigate this? Well, the first thing we might want to do is try to set up a simulation. So could the observed difference be due to random chance variation? We did this with the helpers and hinders an example, and we said, well, babies might prefer helpers versus hinders at no greater level than chance, and so we could just do a coin toss. Well, here a coin toss is not going to exactly work, so we're going to do something sort of like what we did with football temperatures. So what we're going to do is we're going to write our values. We're going to use something like index cards to generate our simulation. So for the football temperature data, what we did is we wrote our data values on index cards. In this case, we don't really have data values. Our response, which would have been like data values, is just whether someone has or doesn't have an earlobe crease. So instead, I'm going to use different colors. So I'm going to have a color for people who do have earlobe crease and a different color for people who don't have earlobe crease. So I've got two different colors. Call them red and black. How appropriate for UGA. I don't usually do that. You should be aware of this. But the question is, how many cards of each color should I use? Should I use 50, so for the 110 patients in the study, should I split it 55-55? So should I have 55 red and 55 black? Should I split it 80-30 to represent the 80 patients with CAD and the 30 patients without CAD? Or should I do it 57-53 to represent the patients who do and do not have ELC? I should do it 57-53. So remember, the first step for the football example was to write the values on the index cards. What I'm doing over here is I'm writing basically doesn't have ELC on these index cards. But instead of writing ELC, not ELC, I'm just going to have red be ELC and black be not ELC. So I just need each color of the card to represent an outcome, one of the levels of my response variable. So this 57 is going to be ELC, and 53 is going to be no ELC or no earlobe crease. So the color of the cards, this represents the response. Just like the data values for the football, this was my response. So what is going on the cards, or what those cards represent, those are my responses. The next step of my simulation is to put the cards together and shuffle. So for the football data, I took all the cards, all those distances kicked, I shuffled them together. In this case, I'm going to put all the cards together, all the red and black cards together, and I'm going to shuffle them. What does this assume? Well, by shuffling, this assumes that having or not having CAD makes no difference. This is breaking the association. This is assuming the null hypothesis is true. This breaks any link between having earlobe crease and having coronary artery disease. The third step in our football kicking example, in our third football kicking simulation, was to deal the cards after having shuffled them into two equal size piles. I dealt into two equal size piles because I had an equal number of hot and cold footballs in that data set. How should I deal the cards here? Well, I should deal the cards into a group of 30 and a group of 80. The 30 represents not having CAD, and the 80 is the patients with coronary artery disease. Because I don't have equal size groups for my categorical explanatory variable, when I simulate my study, I have to make sure that I simulate the imbalance in my actual study. So because there are 30 patients who do not have CAD in my actual sample, I need to deal only 30 cards to one group. The remaining 80 cards are going to go into my other group, and that's going to simulate the 80 patients who do have coronary artery disease in my sample. In my football experiment, after I dealt into my two groups, the next thing I did was calculate the difference in medians. What I'm going to do here is calculate the difference in proportions. That is the sample statistic I am interested in. I want to know, after I've done all this dealing out, what is the proportion of people in the CAD group versus the proportion of people in the no CAD group that have ELC and not ELC. So basically, what's the proportion of, or what is the proportion of black index cards in both of these two groups of CAD and not CAD? I'm going to record that simulated statistic, and I'm going to repeat this, do this 1,000 times. Well, we could do that with the cards, but it's a lot easier to do this in JUMP, so I've generated this. Each of these, so each data point is a P1 hat minus a P2 hat. I've done this 1,000 times. What this does is this assumes that there is no difference, that on average the true difference is 0. So this assumes that earlobe crease occurs randomly throughout the population. That is, it occurs with equal probability for patients with and without coronary artery disease. That there is no association between coronary artery disease and earlobe crease, which is our null hypothesis. So because this mean is basically 0, this mean difference in proportions is basically 0, we have correctly set up our simulation. Let's look at this. Our sample difference that we identified before was 0.6 minus 0.3, or a difference of 0.3. So this is what we got from our actual sample, a P1 hat minus P2 hat of 0.3. Does this seem unusual based on all these many possible sample differences in proportions that we might have observed had we done this many, many times? Well, yeah. Our p-value is 0.003. What we observed is really different than what we would have expected. It's really far away from that hypothesized mean. It's really far away in that tail. So let's think about this. If there really is no association between coronary artery disease and having earlobe crease, we observed a sample difference that would occur sorry, I said this wrong. If there really is no association between coronary artery disease and ELC, we would observe a sample difference of 0.3 or more extreme. So that could be like 0.3 or bigger, or negative 0.3 or even smaller, so like negative 0.4 and so on. Only 0.003 with 0.003 probability. So that would be 0.3% of the time. This is a very rare occurrence. This difference is pretty unlikely to occur just by chance if earlobe crease is not linked in some way to coronary artery disease. Furthermore, this is a pretty big effect. Obtained with reasonable sample sizes. In this case, my effect is P1 hat minus P2 hat of 0.3. This is a difference of 30 percentage points. If you have coronary artery disease, you have 30, I don't want to say that. In our sample, people with coronary artery disease also had, there was a 60% of people in our sample with coronary artery disease also had earlobe crease. That was 30 percentage points higher than people who did not have coronary artery disease. That is a very big difference in probabilities. That is a very large effect. And so because we observed a large effect with a moderate sample size of only 80 people with coronary artery disease and only 30 people without coronary artery disease, and because we have such a small p-value, there is strong evidence to support a relationship between coronary artery disease and having earlobe crease, that is, between coronary artery disease and Frankenstein. We just did this using a simulation study. The next video, we're going to talk about what the sampling or theoretical distribution of the difference between P1 and P2 hat is, and how we can use that to use the theoretical distribution for inference.